Okay, so we're going to continue the second part of part 2. And again, these are the statistical applications for prediction, okay, in maintenance management. Okay, so this one is a queuing theory and applications. So we use this to maintain and also manage the backlog, okay, to have a proper backlog. We always have backlog anyway, any kind of system, and this is just an unfinished work and time to do that job, right? So you have to manage in a proper way to deal with this backlog, and we use something called queuing theory. So the model is you input into the system. So what are you inputting? You input the arriving units, pattern, and then the stability. Okay, of what? Of the things that you need to maintain. Okay, so waiting, line, characteristics. So when you take a look at the line for your service, right, maintenance service, to take care of your equipment, you want to take a look at the length of that line. Is it limited or not? And then you're gonna take a look at the line discipline, which is your order of the line and what's in that line. Service characteristics is we're taking a look at the average service time, so the service time it takes to repair or maintain, okay, the routine checks, maintaining meaning like checking the system, so that time, and then service configuration, also the structures. So everything is involved in the queuing models, right? You don't just do the work in whatever way, you want to do the work in a system, right? And queuing theory is just how do you do that, maintaining or managing. And what are we doing? These are backlog, right? Unfinished maintenance or services. How do we do that? We do it this way. Even that you still have backlog, by the way. So why are we always having the backlog even though we have the system? So the things and the people, okay, working at the company are usually, alright, the factors that is messing up the models or systems. The systems, the models, theories, applications are always near perfect, but who is doing it is the issue. Okay, so therefore we always have backlog, unfinished work, and the time it takes to clear that backlog. Yeah. Again, if you remember, 2 to 3 weeks is the average and acceptable backlog. Okay, management. So how do we manage it? We apply the system, and it's called the queuing models, and we do that. Yeah. Okay, so the first thing we study in the statistical application is service time. How long does it take? Of course, average. Okay, average service time. You have an average because we take this service time data from many different services that we provide in this management. So therefore you have a set of data, okay? And if you pull the historical data, then you have average. And this comes from the actual activity or actual service, and you get that time, okay, average time for that actual service activity, which is your maintenance, and you're handling your backlog. So the probability of service time more than 60 minutes is 0.135. So the probability of service time less than 60 minutes is going to be 1 minus 0.135, and it's going to be 0.865, but they complement to each other. So 86.5% of arriving units will need less than an hour of service time. Okay. So how do we calculate it and write it in a mathematical way? There's a here probability of service time greater than, alright, this time. The x is nothing but it can be any kind of time. In our case, the problem set the service time more than 60 minutes, so x is 60 minutes here. So service time, probability of service time more than 60 minutes. Okay, so this is our original formula that X, it can be any time that is described in your problem. So here is more than 60 minutes, more than 60 minutes. Okay, and it's equal to exponent minus power mu, and then times X. So X is going to be greater than or equal to 0. It cannot be less than 0. It will clash with this formula and will give you a non-logical value. Yeah. So therefore X is greater than 0. And if you want to get the mu, is equal to 1 divided by average service time, because mu can be calculated, right? And that is just 1 divided by average service time, because mu is nothing but the rate. It's a service rate. Okay, mu. So it's very similar to the reliability that we usually calculate. So if you remember the lambda, we use a similar formula because they follow the same pattern, right? So we can use the same function like that. So here, that's the rate and that's the time. Okay, the rate, the time, and this rate can be failure rate. This rate can be, in this case, the service rate. This rate can be reliability rate. Okay, anything that you want to do. So at that time, we use a little function like this, right? A little function like that, and then we have a t, right? And then we go equal to, and then e to the power, and then minus, and this is the rate, and then that's the time. Okay, and this function can be failure. Okay, like that. This function also can be a reliability. So anything that you want to calculate. We didn't teach you this in this case. Let's go directly. The function is reliability. Go straight in, yeah, to calculate that. Okay, now the rate is we're looking at service, so therefore service rate. And then we're looking at the time, so therefore we use the same exponential formula. And mu, you can calculate 1 divided by average service time. Average service time is 30 minutes. Okay, so this is given to you in the example. So therefore, assume the average service time is going to take you 30 minutes to do that job. So if you want to find the probability of service time, okay, probability is nothing but it's just an event. So if you want to find, so what is the percentage of the event of the service time that can be more than 60 minutes? Okay, so that's longer service time. Usually it takes only 30, but now 60. So you know how much percentage that can happen, okay, at your company. So you calculate E is 2.718, that E, right, to the power minus, okay, your mu is 1 by average service time. Average service time in this case is 30, so 1 divided by 30 times, we know it's going to be, service time is going to be greater than 60 minutes, okay? So you multiply with 60. So you're going to get 0.135. So that's what we're saying right here, yeah? 0.135. If you transfer that into percentage, that's 10, so 13.5%. From decimal to percentage. I'm not going to show you anymore because just by looking at it, you should come up with the percentage right away, okay? So now we're going to take that out from 1 and you get 0.865, just like we do the reliability and failure, the same thing right here. So the service time, okay, less than 60 minutes is going to be that. If we go in detail, it's going to be service time less than or equal to 60 minutes is going to be this, okay? Because there's a equal to sign is also there. But if you go superficially, we can also report that way. It's not that strict anyway. So 86.5% of arriving units will need less than an hour of service time, okay? And about 13.5% of the arriving unit is going to take more than 60 minutes of the service time. Normally, it's going to take only 30 minutes of the service time, right? Sometimes this can happen, and sometimes that can happen, yeah? So if you want to take a look at in a time diagram like that. Usually it takes only 30 minutes. Okay, now you have 60, so that's a double. So usually most of the service average is 30 minutes. Okay, so altogether from here to here, let's say that's a 60 minute. From here all the way to there is 60 minutes. Sometimes it can be less than 60 minutes, and sometimes it can be more than 60 minutes. Okay, more than 60 minutes, it can happen 30.5% of the time of the arrival unit, and about 86.5% of the time is going to be less than 60 minutes. Okay, and that's how you visualize what you're calculating in this exam. Alright, so let's go to the next one. So here's another curve right there, and we're studying probability against time. So probability going up this way, time going up this way. So we have three different service time. At 30 minutes is this one. Sorry, this one. And service time 60 is this one. Service time 90 is this one. Okay. So the service time going up 30, 60, and then 90 this way. Okay. And when you look at the probability, okay, the event that can happen is going down as time goes by. Yeah. So these are arriving units on this little thing right there, or units right in there. So service time is described by a negative, again, negative because it's going down that way, exponential probability distribution. Okay. A positive exponent, if you remember, go that way. This one is a little bit curved. So there's a little bit because of the function that's going on. Okay, it's a little bit curved because we're dealing with the service time in the function of the rate, which is your minus e to the power minus mu, and then time. Yeah. So review your mathematics calculus so that when you take a look at the formula, you can be able to understand. If you're kind of raw and you didn't study in a high school and didn't know the calculus, I recommend you to take calculus 1, 2, and 3 to be able to understand it. And if you need help, please come and see me so I can explain that to you. But it's going to take you some time to be able to understand the function of time. Right? All the activities are happening. And when the activities happen, we can be able to measure from the beginning of the activity to the end of the activity, and we call that time. Okay, so time exists only in our head. Okay, it's not a physical thing. It is the events that is happening with our physical nature that we know in this world. Yeah, so therefore it is not something that is absolute. That is something that we name. Okay, there are many things that we name by using a language. So anyway, I don't want to go into the deeper science or the philosophy because it's gonna confuse you. So we just come back here, and service time again is going to be a negative exponential probability, and we are looking at the distribution of the arriving units. Arriving units right there. Okay, here are the arriving units right here. And these units is going to take 30 minutes, and that unit is going to take 60, and that unit is going to take 90 minutes per service. Okay. Configuration. How are we going to run this service? So we have to configure, meaning like how are we going to do it in the queue, but with using the queue model. So the single channel. So here, arriving unit, you have to do the service for this, service for that, service for this, and this, 4 of them in queue. Okay, we're going single phase, going in this direction, one after another. We have a single channel, so we have multiple phases here, 1, 2, and 3. So this one is going to go into this, this, and that. So multiple phases in service. You have a multiple channel, it's going to go to 1, 2, and 3, but they're going to go through only a single phase. Okay, we have a multiple channel and we have multiple phase. So this one is going to go bang, and then going to go into here, going to go there, going to go right here, and then right here. So you follow the arrow, yeah, and then go that direction. It's a little bit complicated. So phases are the service, different services that you're doing in this combination of services. Okay? So these are my arrival units, and these are our service facility that they are performing a particular service. Okay. So the number of phases, interaction points between the arriving units, and the number of services. Okay, so that's what we're looking at in the service configuration. I just want you to know, okay, about that, and don't try to get everything by heart. If you know this, you can be able to understand, okay, the patterns of how it goes. It's pretty easy. Like phase, you have different phase, multiple mean different phases, single mean just one phase. You have single, one phase. Okay, we stack them up, and then it's going into multiple channels. Go into a single, right? Arriving unit is going to get into multiple channel, and then you also have the multiple phases right there. Yeah, this is really complicated. Okay, then we will continue the queue and the queue models and how we manage them. So machine waiting the repairs, equipment needing preventive maintenance, routine, they all have to wait in line to get a service. Since they all have to wait in line, we call that queue in line. Since they are in queue, we have to use a queue model to service them. Yeah. So queuing model characteristics. So the average number of the units. The average number of the units that you need to service, we call them customer. So don't try to think the customer is the people. No, customer can be the equipment right there, right? Waiting in the queue for service. So the average number of units in the system, all right, waiting and being served. What kind of system? Not the production system, maintenance system. Yeah. So you are giving maintenance service to these units. So the average time each unit spend, okay, waiting in the queue, the average time each unit spends in the system, wait and service time, we call that. And then the probability that the service facility is not working, which is idle, waiting here. The probability that an arriving unit will have to wait. And then the probability of specific number of units in the system. So anyway, these are the characteristics of our model. So what are we doing? We are carefully studying each one of them. Okay, they're all values. Average number of units, okay, average time, again, probability, events, yeah. So I bold these, okay, characteristic like that. So just by looking at it, you know the service that you need to give units, yeah. Units meaning like the equipment that you need to repair or maintain, okay, give maintenance. And the time is going to take, and then the events that can happen, yeah, in the service facility. So every time you have a unit coming in for service that is in a queue, so therefore queue model, you have the average time going to wait, or average time is going to be in service, yeah. And what can happen events at the service facility is the unit will be idle, the unit will be waiting, or the unit will be in a system, service system, yeah. That is all you can do anyway. What can you do more than that, right? Okay, so basic queuing model calculation. How are we gonna calculate that? So we're gonna start with first breakdown enters the waiting line, okay, at the rate of 3 per day. So the breakdown meaning like either units that need to be repaired or maintained going to enter the queue. And it is coming in at the rate of 3 units per day. Okay, so I have 3 units per day, and I use the arrival rate, which is lambda. Don't get confused with the failure rate. It isn't. We're not dealing with the system. We are dealing with the queue at the maintenance facility arriving. Okay, so we call the arriving rate lambda 3 per day. Service rate mu, that is 4 per day, because it said it so right here. So the average repair time is going to take 2 hours to take care of the breakdown, 2 hours. So an employee in the service facility, they're going to work 8 or 10 or 12 hour shift. So in this case, it's 8-hour shift. So the service rate that employee can do to take care of this maintenance is going to be 4, only 4, okay, the maintenance technician can do. So how do we get that? 8 hours of his work day divided by 2 hours for each repair. So therefore maximum, if he is working continuously all 8 hours, he can repair 4, okay? But nobody works 8 hours straight. They have to go to lunch, they have to do something, go to restroom, right? Refreshment, all that. So you're between, all right, between 3 and 4 if you're efficient. Yeah. So therefore service rate is 4. Again, we have to calculate the maximum and the minimum. So we always calculate the maximum. So that's a 4 per day. Arrival 3 per day. So the question is, what is the average number of units waiting to be serviced or repaired? We want to know the units in the queue. We have a symbol for that is L. So L is the unit waiting to be served. K in the queue equal to lambda squared divided by mu, and then mu minus lambda. We know this, that's 4 and 3, so put that. Calculate it, and you're going to get 2.25 units. I will give you the formula. You only have to calculate. You have to come up with this 2 number correctly in order for you to put the data right in here. Okay, so you will get the correct calculation or the result. If you do this thing wrong, you're not going to be getting the right, okay, result. So therefore, please study this, and this will be in your midterm and the final. You don't have to remember any of this. I will give you the formula, okay? But you know L, okay, is this average number of units waiting. That you have to know, okay? You have to know mu is arrival, and lambda is arrival, and the mu is a service rate, okay? And then calculate. So when you use your calculator, make sure you actually, pressing the button, all right, to calculate correctly. Sometimes you will have error if you don't do it carefully. That's why some people are getting a wrong result, even if doing the same procedure. Okay, second question, what is the total number? We are looking at average. Everything is average anyway. Units that are either being repaired or are waiting to be repaired. And now the L, units being serviced. Okay, S is going to be in service. We already know this, put it in there. The formula is a little bit different, and you get 3 units. Then we're going to take a look at the average wait time. All right, number 3, the characteristic in the queue model. So we are calculating one by one. This time we call that the average wait time is W in the line. All right, Q is for Q again. Similar formula, input the same values, and you're going to get this. But this time we're dealing with the time. So 0175 is 3 by 4 of the day, and you have 6 hours out of 8 hours, right? So 75% of your 8 hours day is going to give you 6 hours, right? And that's your average wait time in the line. So averagely, an arriving unit must wait nearly 6 hours before any repair work can start. So this is the average time in the queue. Okay. Okay, then we have what's the average total time in the repair shop? The next formula, the same thing, input it, calculate, you get 1 day. Okay, so average total time in the shop. So the actual repair time is going to take 8 minus 6 from the less on number 3. You will get 2 hours on the average. So the repair time is take 2 hours for each unit. 1 day, okay, here you will get the 1 here. So that's W is the wait time in line. So that 3 unit, arrival 3 unit, okay, got to wait about a day. Yeah, for each unit got to wait a day. So that's 8 hours. Because it takes about 2 hours to repair one. So what's the probability that the maintenance department is idle? So that's your probability. 0 mean not doing anything, so therefore idle. So 1 minus lambda divided by mu is going to give you, we use the same value, will give you about 25%, right? So that means 25% of the time the maintenance department is idle. So the service department is idle 25% of the time in an 8-hour day. So what's the probability that an arriving unit, okay, that need to be repaired or maintained will have to wait in line for service? So we use probability lambda divided by mu. This is arrival, okay, service. So 3 by 4 and you're going to get 75%. So there is a 75% chance that the arriving unit will have to wait for the service. Because you have only 3, right, arriving out of 8, okay, hours day, and 2 hours it takes to repair one. So therefore 75% of the time you will be waiting. Yeah. So what are the probability that a certain number of units are in the system? So P again, probability, N is your unit in the system. We calculate with a different formula. And then you'll be getting, we'll use the same thing. And you'll be getting 0.14 times, as that's a 14%, okay? Times 100 will give you 14%. So what is the probability that 2 units are in the system? 3 divided by 4 squared times 0.25, okay? So that will be the probability of the 2 units in the system, a 14% chance. So sometimes a student, based on last semester, don't understand what the system means. This is not the production system. This is at the maintenance department doing the service. Okay, so we're dealing with a service system. So don't forget that. So this mu is a service rate, and then the lambda is your arrival rate. Okay, we're repairing or maintaining the equipment at that department, and that is your system. And if you want to know a certain number of units, okay, so how many of them? 2. So all you have to do is put 2 right at N. So the units in the system, 2 of them. So what is the probability, okay, that 2 units are in the system? It's going to be 14% of the chance. Okay, you will be doing the first and the second, all right, arrival unit or service. That is very low, okay? Alright, so that's it for this chapter.